Hello and welcome again to my Physics Online video lecture series. Today's video, we're going to be revisiting Ampere's law. This is, of course, from an algebra-based perspective. Ampere's law, you'll recall, was basically applied to simple situations. It's generally applicable, but we usually apply it to simple situations such as a wire that's bearing some current. We take an Amperian loop around the wire like so, and then we basically say that if you add up the dot product between current and length around the wire, so basically like displacement vectors, like this little delta L right here, that should be equal to the permittivity of free space times the enclosed current. Now, the assumption with this setup is if I have a Amperian loop like this, we've thus far mostly assumed that the enclosed current has to puncture through this flat area enclosed by the loop. So any current passing through this flat area should be enclosed current. With that said, the Ampere's law does not actually require that our enclosing area be flat. We could have chosen basically like a sphere like this and said how much current is passing through this sphere. And we would have basically come up with the same answer in the case of this wire, because if I were to make a little dome here, the dome would still have the wire passing through it. And as long as we're somewhere within our wire like that, it's all fine. Even if the wire bends somewhere, so even if I come up here and say, okay, well up here the wire bends off like this, that's fine, because if I stretch my dome up far enough to where the wire is bending through it, it still bends through one of the sides. And so no matter what you do with this wire, the same amount of current passes through it. However, what we did not consider was what would happen if we had a natural interruption in the wire. For example, maybe the wire sort of terminates in a pair of plates like this. So I have one plate here, the wire kind of terminates on it, and then down here somewhere I have a second plate and a second wire passing out of that second plate. Now if I've got current running through the wire, say like this, current basically runs here, current runs here. If I were to pick any location along this wire and do like a flat versus dome, as long as I'm out here, Ampere's law works fine as is. What would happen, however, if I picked as my Amperian loop this space right here that's between the two plates? I'm going to actually use green now to fill in the area. Well, in this region right here, there isn't any current, or at least no current carriers pass through, and so we should have an enclosed current I enclosed of 0. On the other hand, if I draw an elongated dome like this that passes through the wire in this sort of fashion, then my enclosed current for this dome area is no longer a 0. The dome area actually sees an enclosed current, I enclosed, equal to I. Both have the same Amperian loop surface, delta B dot L. So somehow we need for delta B dot L for this sum to equal 0, and for this sum, b dot delta L, to equal I, which is not 0. So there is an apparent contradiction. Now this apparent contradiction was kind of brought to mind by none other than James Clerk Maxwell. Now Maxwell not only came up with this problem, he also found a possible solution to it. The possible solution is this. Consider maybe a side view of these two plates. So I've got a wire running in to this plate like so. I've got current coming in, and then down here I've got my second plate like this, and I've got current, whoops, that's not a very good second plate though. Got current running in to this second plate like this. So I from here is coming out of the plate, I is going into the plate. As this happens, I basically start getting plus charges to build up on the top plate, and I'm essentially removing the plus charges from the bottom plate. So I end up getting a bunch of minus charges like this along the bottom plate. Now you'll recall that the electric field between two parallel plates basically runs from the plus side to the minus side, and essentially ends up being proportional to how much charge is on each plate. Specifically, if I was going to describe the electric field here using Gauss's law, E would look like Q divided by plate area over epsilon naught, or in other words, it's sigma over epsilon naught. So each of these plates has area A. So area A, area A. All right, so as I start running current through this, I increase the values of Q. So I changes Q, either increasing or decreasing. In this case, it's increasing. And that in turn means that I changes E. So E is going to be increasing. In fact, we can see that since this is a true statement, that I is proportional to E, or really to the rate change of E. But maybe we could say I times T is proportional to E, and I is proportional to the rate change delta E over delta T. In other words, I is equal to some constant times delta E over delta T. Okay. Now it turns out that that constant is actually epsilon, the permittivity between these two. And we can see that because if I multiply I by delta T, I'm going to end up getting Q. So I delta T is equal to Q as an order of magnitude thing. If it's a non-constant current, then I kind of have to do like an area under the I versus T graph. Okay. So I'll call this area under I versus T. And so basically this means that I should be equal to, if we've kind of solved all this stuff in terms of E, epsilon naught, we got to multiply both sides by an epsilon naught, and we got to multiply both sides by an area. So epsilon naught delta E over delta T area. And this basically is the solution that Maxwell came up with. Essentially, Maxwell's solution is that there are two types of current. We have carrier current, and carrier current I is just defined as essentially like number of charges times how much charge each particle has divided by the amount of time that this has taken, or delta n q over delta t. And this is the same equation for what it's worth, where you're using like lowercase n times drift speed times charge per particle, etc. So there's carrier current, and then there's also what's called displacement current. And displacement current is taking this equation here and modifying it slightly to recognize that this is actually a dot product and that this change is actually the change in the dot product. Okay, so coming back over here to the displacement current, we could call this like I sub C. I sub D would be epsilon naught times delta of the flux of the E field over delta time, where flux of the E field is just the E field dotted with the area vector of the surface that you're taking the current flux through. Okay, end result is that the Maxwell Ampere's law looks like this. Maxwell Ampere's law says sum of the dot product between the magnetic field and the little displacement vectors around a closed loop. So let's use an index of J for this, around a closed loop, is equal to the mu naught times the carrier current plus mu naught times the displacement current. Or if you prefer, this is mu naught times I enclosed plus mu naught epsilon naught delta of phi E over delta T. This is a delta. Okay, and so this is what's called the Maxwell Ampere law. This resolves this weird problem that Maxwell came up with that involves current in the presence of a capacitor and magnetic field in the presence of a capacitor. Among other things, it allows us to use Ampere's law to find what the magnetic field strength is in this region between the two plates. The other thing that it basically allows us to do is, complete Maxwell's law as well. And it has an interesting consequence. So the interesting consequence is that changing an electric field produces a magnetic field. So change E, produce a B. And that is kind of the complement to Faraday's law, which says that changing B, the magnetic field, causes a change in A. And that's the real significance of this discovery, because taken together with Faraday's law, taken together with Gauss's laws, you get what are called Maxwell's equations and the prediction of electromagnetic waves. So that's it for today.